Welcome back, everyone. Today we're going to go through how to export the data we collected in the last video, as well as how to prepare a simple calibration curve that you can use to extrapolate recorded currents to concentrations. In order to export file information, you will start by clicking on the File button in the top left corner of the screen and open the desired file. From there, you will press Find Max or focus on whatever area of the file you are interested in exporting. By focusing on this area of the color plot, you will receive two important pieces of information. In the middle is your current versus time trace with current on the y-axis and time on the x-axis. This reveals information regarding the release and reuptake measurements for your analyte. To export this information, you will right-click on the line and select Lines and Annotations, then PGL Gradient Line, and finally Save TSV. This will generate a notepad file that can be copied into analysis softwares such as Excel or GraphPad. For the sake of this video, we will be copying the current versus time data into Excel to relate current to concentration. On the right is your cyclic voltammogram, or CV, with current on the y-axis and voltage or potential on the x-axis. And this reveals qualitative information about which analytes are present in the mixture and can be used to verify an analyte's identity when working in a more complex mixture. We won't be analyzing this information today, but it can be exported as well for other analyses. Now I've prepared an Excel file where I can copy and paste the information I've exported from the software for each concentration of dopamine. So I'm going to start by opening a representative current versus time text file and copy the contents to paste the information into the spreadsheet, labeling it accordingly. Once all of your data is copied into the spreadsheet, we are going to find the average current at each time point for each concentration of dopamine. Once that is complete, we are going to find the maximum average current for each concentration. We injected our analyte 5 seconds into the recordings, so our peak current will be a couple seconds after that time point, but yours will depend on when you injected your sample. Here I have written down each concentration of dopamine with its corresponding average maximum current. The concentration of dopamine will become our x variable, while the maximum current will become our y variable to correlate the two variables in a calibration plot. For the purpose of this video, I will just make a simple scatter plot to highlight this relationship. From this plot, we can see that current linearly scales with concentration of dopamine, and there is 0 nanoamps of current with no dopamine present, which is important for allowing us to extrapolate current to concentration. A linear regression of these data can reveal the linear equation, and you know your data fits the equation well when you have a coefficient of determination or an R squared value close to 1. The slope of the line is in nanoamps per nanomolar, which can be used as our calibration factor to relate current to unknown concentrations. For example, 10 nanoamps of current on this electrode is equal to about 210 nanomolar of dopamine. These calibration factors are incredibly important because each electrode has different sensitivities to each analyte, making these calibration plots a fundamental part of FSCV data analysis. Today, we just showed one example of how you can export and analyze your FSCV data to allow for more complex studies. These data can be easily analyzed in other software such as GraphPad and MATLAB, providing the opportunity for you to tailor this process based on your specific needs. Thanks for watching, and I hope you found this helpful.